Then
inodes.
And then the blocks. So that's the way a typical hard drive is partitioned, okay, under the Unix file system. All right? And so, what is the constituency of the superblock? Does anybody remember? Sure. So it's got the number of inodes. Okay, it's got maybe the top of the inode list. All right, and the list itself. It could have other things. The inode list. All right, so something like this. The number of inodes, where the top of the list is, and then the inode list. And there may be other things as well. But conceptually, it's a way of figuring out what inodes are available. All right? Good. And then what else is in there?
The free blocks.
Same thing for blocks. So, you know, number of blocks. Okay. Top of the list. Okay. And then the block list. And maybe some other things as well. So, and then, so what is this really? It's just like a table of contents of sorts. Yes? Now, somebody describe the partitioning of this inodes. What is it?
Which one know what's inside?
Inodes, what is it?
That's just a counter itself. I mean, that's a counter for the inode number.
Okay,
it's an
you can
index.
think of it as being, yes, I understand what you're saying. It's just a series of inodes. It's carved up into equal-sized chunks, starting at, say, 0, and ending at whatever the number of inodes is. All right, so an equal number, so some number of equal-sized little chunks. Right? All the way down. Right? And then what about blocks?
They contain data.
Same kind of a deal, right? Same kind of deal. Maybe different size, but just a series of blocks. And the inodes might start at 0, and they might go up to m sub I minus 1. The blocks might start at 0, and they might go up to m sub b minus 1. So there are m sub I inodes, m sub b blocks. Arbitrary notation. I could have called this Fred. I could have called this Harry if I wanted to. It doesn't matter. Right? It's some number of inodes, and that's one of the things that's in the superblock. How many inodes are there? And then where's the top of the list start? Then there's the list itself. So 0, used. 1, used. 2, free. 3, used. 4, free. 5, free. Blah, 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 blah. Like this.
Dr. Morris, basically all, of course, I have virtual memory. So for my presentation, I had virtual memory. So I'm just looking at all different operating systems. And there's a bunch of them. All of them basically sit up the same way with the same.
Yeah, that's not to do with this. This is file system, not virtual memory.
But it does with the operating system, right?
There is a similarity, but it's not the same.
Okay.
So we'll talk about it later. It's not the same. So this is disk space, all right? So good. Now then, let's talk about these inodes. What are inodes used for? What's the principal purpose of an inode?
The addressing.
It's the start of a file, right? Okay, so in some sense it's the start of a file. So every file corresponds to one inode. Does that make sense? Every file corresponds to one inode. What kind of files are there?
They can be data files or it's another.
There are, so in the files are what?
The directory
They're directory files.
files. Ordinary files.
There are ordinary or regular files. And then what?
Special files.
Special files. Special files. All right, good. So, we understand the notion of data in an ordinary file.
Right.
What is the notion of data in a directory?
The idea is going to
It
correspond
just-
to another.
It's a list of names and inodes for other files. Does that make sense? Okay, good. So then, let's look at the structure of an inode. What does an inode look like?
It has size, type.
Metadata.
So you could roughly partition it up into two pieces, right?
Right.
And the way I've been doing is in the top half, and Asma said up here, this is metadata. That's data about the data. Okay, so what are some examples of the metadata in an inode?
Size, type, type of yeah.
So size, type of file, what else?
Address one.
Well, that's downstairs.
Okay.
What else?
Just attributes, like what type of file?
What else? So, yes, so
The file
size, type.
itself. The file itself, like,
The I know.
the file name or the
Well, the name is in
the type.
Is in, so the type we've already got.
Okay.
What else?
Isn't the number of the I know represented in the top two?
No. Come on, what other attributes might a file have?
Here,
Oh,
Huh?
right,
I mean, the-
read,
Parent and
the
child.
parent,
Permissions,
yeah,
right? Who can do what to the file, right?
so you can read or
And
write.
what other kind of information might it have? Yeah, timestamp, right? Timestamp. Okay? And various and sundry other pieces of data, metadata, that talk about the file. Then, what's down here?
Addresses.
A series of addresses. Now, depending on the way the file system's set up, okay, they could be all direct addresses, there could be 5 direct addresses, 2 single indirect, 3 double in, it depends, right? I mean, I could make it, if I were the file system designer, I could make it any way that I wanted to. But the basic idea is that it's a series of addresses. So suppose I had address 0, address 1, address 2, address 3, and then I had single indirect 0, single indirect 1, and then maybe double indirect 0, double indirect 1. What does that imply?
That
was
implies.
the structure of the file system. So it's got 4 direct addresses, and each of those point to what?
In
One of these blocks. So there would be some address, some address, some address, some address. And when we say address, what do we really mean? A block number. Now, how would it know what block number there is?
because
It would go to the operating system. The operating system would interrogate the super block in the block list, and it would find a free block. It would give that number back, then it would
take it off the list.
It would, in the list, it would say this is no longer free. So each of these would point to a block. Now, what about these single indirects? They also point to
A block
blocks.
that points to
But the difference in these, where do these point to?
data
These
blocks.
point
Da-
to
data
data
blocks.
blocks. Okay? They all point to blocks, no matter what. Okay? So data, data, data. Now, where does this one point to? It points to a block, but how is that block used?
to point to an
Addresses.
It has a list of addresses in it. So it's got, you know, address 0, address 1, all the way down to some address K, let's say. And then each of those in turn does what?
to another block.
Points to a data block. Do you see it? Is it clear?
Yes.
And then what if I had double indirects? What would happen with those?
It would point to
Again,
a
addresses of blocks. Yes? And then those would point to
block
a block.
that points to a block.
Okay, with addresses, A0 down to AK, and those in turn also point to additional blocks, A0 all the way down to AK, and then finally
It points to a data block.
to data, right? You see it? So it might have only single indirect, it might have single indirect, double indirect, could have triple indirect, could have quadruple indirect, you could have whatever mixture the particular file system designer chose. All right? Good. So then, suppose that I wanted to, I'm in some I'm in some current working directory. And I want to create a new file, all right? Since I'm in that current working directory, what's available to me already?
iNodes.
Not only the inode of that directory, but
The addresses.
the directory itself. And in the case of a directory inode, what does the data associated with that directory correspond to? We already mentioned it before.
Meta.
It corresponds to the listing of the directory. Yes? So
Oh, yes.
if this was the directory, let's say it was slash home/grm. All right? So where's this inode?
The root directory?
Yes, which is where?
In the super.
0.
0, yeah.
So what would it do? So we're going to now play the role of the file system. Okay, you're going to be the person that gives me the inode. All right. So that means you're some little tiny routine way down in the bowels of the operating system, and I say to you, give me the inode 0. Okay, then what would you do?
I'll go to the...
You would go to the inodes on the disk.
Uh-huh.
You would find all the ones and the zeros that are in this chunk of data recorded on the hard drive, and you would return them to me. Does that make sense? I'm not saying give me a new inode. I'm saying give me inode 0.
Okay.
There's a
So what
difference.
if I don't have inode 0?
Well, you would give it to me anyway.
I'll
There is an inode 0.
So I'll free it first?
Oh,
No,
because
no.
the,
You're not interrogating whether or not what I'm asking for makes sense.
okay.
So one function would be, give me the inode number n, whatever that is. Another function would be, I need an inode, in which case you'd look in the free list and you'd get me one that's free.
So you give me specific iNode when you say the
Yes.
first one.
What if it's not free, right?
Yeah.
Yes,
It doesn't matter because it would create one, right?
in the case of the function we're talking about, it wouldn't be free if I was asking for it, presumably. If I say, give me inode X,
Okay.
theoretically then, inode X
Must be free.
has some data associated with it.
Yeah.
So, what are some of the functions that I would need? So I would need something like this. Read inode. Agreed?
Yes.
And what would this be? Some integer x. Okay, and what's it going to return? It's going to return an inode. Do you understand? So it's going to return an inode, whatever that means. Okay, that's some data structure that looks like this. Okay? Some data structure that looks like this. So in C, it might be something like, struct inode. With brace and what? Int size. Char type. Perm 8. Time T. Timestamp. Long A0. Long A1. And the structure, right? Something like that. A record type. Okay? Okay? Looks just like this, doesn't it? Except now I've mapped it onto something that looks like C. All right? And so what would this function over here do? I would give it an inode number X. It would go to the disk drive, find inode number X, read off all the information that's in that, and populate one of these objects and return it to me. Does that now make sense? All All right, so that's one function I might need. How about this one?
Right?
Right. inode.
When you
In
need,
this case, int x inode node.
Dr. Morris, when you need to execute to?
No, no. You don't execute an inode. So what? And by the way, what's the return type of this? Probably either int for an error code, or we'll just say void. Right? It doesn't return anything, simply does something.
Okay.
What does it do? It takes the contents of this inode, one of these structs, yes, and it records it here at the specified inode number. And we're assuming an int works. It might need a long, or it might need a long, doesn't matter. Okay, doesn't matter. Probably it's a long or a long with the large drives we have nowadays. So what other kinds of functionality would I need down in the bowels of the operating system? How about int get free
No.
inode void? Yes? Wouldn't I need to get a free inode? Maybe I'm going to create a new file. Where do files start?
For free, I know.
With inode numbers. So I need to get a free inode. So what would this function do down in the bowels of the operating system?
Go to the disk and see what the free I
Go
knows
to the
is.
super block and look in the inode list.
Get a free I
You'll
know.
find, say, the first one that's free. Record its number. That will be my kitchen pass expiring.